The critical role of base cases in recursive algorithm design. Recursive algorithms form the backbone of many advanced computational problems by breaking complex tasks into simpler subproblems. However, their power hinges critically on well-defined base cases that prevent infinite recursion and ensure termination. Understanding how these fundamental elements function is essential for anyone aiming to master recursive problem-solving techniques. In any recursive implementation, the base case serves as the stopping condition that prevents the algorithm from entering an endless loop. This critical component determines when the recursion should stop executing further calls and begin returning results back up the call stack. Without properly defined base cases, even seemingly simple recursive functions can lead to catastrophic failures such as stack overflow errors or incorrect computations. Understanding recursion fundamentals. A recursive function consists of two primary components, the base case and the recursive step. The base case defines the simplest possible scenario where the solution is known without requiring additional recursive calls. In contrast, the recursive step involves decomposing the current problem into smaller instances of itself. For example, consider calculating factorial n using recursion. Here, the base case would typically be when n equals 0 or 1, since both return a value of 1. The recursive step then computes factorial n1 multiplied by n. This decomposition continues until reaching the base case, which provides the terminal result. This structure ensures that each level of recursion contributes meaningfully towards solving the original problem while maintaining control over program flow. Properly implementing both aspects guarantees correct behavior across various input sizes and types. The significance of well-defined base cases. Base cases play a pivotal role in ensuring the correctness and efficiency of recursive algorithms. They act as safeguards against potential issues arising from unbounded recursion depth. When designing recursive solutions, developers must carefully identify scenarios where no further breakdown is necessary. Failing to define appropriate base conditions often leads to infinite loops where the function keeps calling itself indefinitely. Such situations not only consume excessive memory but also risk crashing applications due to exceeding maximum recursion limits set by most programming environments. Consider an improperly implemented Fibonacci sequence generator where the base case might mistakenly check for values less than or equal to 1 instead of exactly 0 and 1. This subtle error could cause unexpected behaviors depending on initial inputs provided during execution. To illustrate this concept visually, if base case returns when n equals 0, correctly terminates at 0 if base case checks and missing base case entirely, leads to infinite recursion multiple overlapping bases, introduces complexity in debugging. Careful consideration of edge cases helps avoid common pitfalls associated with recursive implementations. By establishing clear boundaries for what constitutes a solvable instance within our function's domain, we significantly reduce risks related to erroneous outputs or system instability. Common patterns in base case implementations. Several standard patterns emerge when defining effective base cases for different types of recursive problems. These conventions help maintain consistency and predictability across diverse algorithmic approaches. One prevalent pattern involves checking for empty data structures before proceeding with recursive operations. For instance, when processing lists recursively, an empty list indicates there are no elements left to process, thus serving as a natural endpoint for computation. Another frequently used approach focuses on numerical thresholds rather than structural properties. Many mathematical recursions utilize specific numeric ranges as indicators for halting further divisions of the problem space. Examples include factorials, exponentiation calculations, and geometric series summations. Additionally, some algorithms require multiple distinct base cases to handle varying degrees of simplicity effectively. Binary search trees provide excellent examples where nodes with no children represent leaf-level terminators, whereas single-child nodes necessitate separate handling mechanisms. Identifying these recurring motifs enables programmers to apply generalized strategies whenever confronted with new recursive challenges. Recognizing familiar signatures among existing codebases accelerates development cycles through reusable logic constructs tailored specifically toward termination assurance. Analyzing real-world applications, real-world software systems extensively leverage recursive methodologies supported by robust base case definitions. Web scraping frameworks employ depth-limited traversal strategies where pages beyond certain levels trigger automatic cessation of exploration efforts. Data compression libraries implement Huffman coding schemes relying heavily upon end-of-stream markers functioning akin to traditional base conditions. These signals instruct encoding routines to cease appending symbols once they've processed all relevant information contained within source files. Operating system kernels manage directory tree traversals utilizing folder access permissions as implicit constraints governing recursion progression. If user privileges prohibit accessing deeper folders, those directories automatically become de facto endpoints terminating respective branches of investigation. Game engines utilize recursive pathfinding algorithms constrained by terrain impassability features preventing unnecessary state expansions along unreachable routes. Such limitations inherently serve dual purposes, acting simultaneously as performance optimizations and logical conclusion points. These practical applications demonstrate how real-life constraints naturally evolve into functional base case implementations devoid of arbitrary artificial restrictions imposed solely for algorithmic completeness' sake. Performance considerations in recursive designs. Evaluating performance characteristics becomes crucial when developing high-throughput recursive algorithms. While recursion offers elegant expression capabilities, its inherent overheads demand careful optimization considerations. Each recursive invocation incurs significant runtime penalties due to repeated context switching between frames on the call stack. These transitions involve pushing local variables onto temporary storage areas followed later by popping them off after completing nested operations. Memoization techniques offer viable remedies for mitigating redundant computation costs incurred through repeated evaluations of identical subproblems. Caching intermediate results allows skipping expensive recalculations, thereby improving overall efficiency dramatically under particular usage scenarios. Tail recursion represents another promising avenue worth exploring, especially within languages supporting native tail call optimizations. By restructuring code so that final action performed inside each recursive frame corresponds precisely with subsequent invocations, compilers can eliminate superfluous stack allocations, resulting in linear space complexities comparable to iterative counterparts. Benchmarking exercises reveal substantial differences in execution times between naive versus optimized versions, highlighting importance placed upon thoughtful architectural choices influencing ultimate performance outcomes. Debugging challenges specific to recursive code. Diagnosing issues within recursive programs presents unique difficulties compared to conventional procedural paradigms, primarily because of layered nature of call stacks involved. Traditional debuggers struggle displaying meaningful insights regarding deeply nested sequences, causing confusion amongst novice developers unfamiliar with tracing multi-tiered executions manually. Visual inspection methods prove particularly advantageous. Here, offering intuitive representations mapping out hierarchical relationships forming entire solution landscapes visually comprehensible even without prior exposure to formal computer science principles. Instrumentation tools equipped with specialized profiling modules enable pinpoint identification of problematic regions, contributing disproportionately towards increased resource consumption. Metrics monitored continuously throughout testing phases. Implementing defensive logging practices proves invaluable during early stages, helping isolate exact locations responsible for divergent behavioral patterns observed across varied test suites executed sequentially under controlled experimental settings. Best practices for writing effective recursive functions. Following established best practices significantly enhances reliability and maintainability attributes characterizing professional-grade recursive implementations. Always begin by thoroughly analyzing target problem domains, identifying core decomposition rules applicable universally irrespective of individual problem variations encountered routinely during development cycles. Design modular architectures separating concerns, clearly distinguishing responsibilities assigned explicitly either to base condition handlers or recursive expansion mechanisms facilitating future enhancements effortlessly without disrupting existing functionalities prematurely. Employ rigorous validation protocols verifying output integrity, consistently validating against expected outcomes derived mathematically confirming accuracy of proposed solutions independently from actual runtimes measured empirically through comparative analyses. Document meticulously documenting rationale behind design decisions, providing sufficient contextual background enabling successors comprehend underlying motivations driving particular implementation choices made judiciously considering trade-offs evaluated systematically beforehand. Evolution of recursive programming techniques over time. The field has witnessed remarkable transformations evolving substantially alongside broader technological advancements shaping modern computing ecosystems, profoundly impacting how practitioners conceptualize and execute recursive processes today. Early Lisp dialects pioneered widespread adoption of recursive constructs, establishing foundational theoretical models still referenced academically despite rapid obsolescence affecting legacy implementations gradually phased out, replaced progressively by contemporary alternatives better suited addressing present-day requirements, dynamically adapting fluidly amidst changing environmental demands. Functional programming languages continue promoting idiomatic use of recursion, emphasizing purity advantages inherent in immutable data structures, reducing side effect occurrences commonly found pervasively distributed across imperative style applications burdened excessively with mutable state management complications, exacerbated exponentially scaling concurrency intensities surpassing manageable thresholds easily exceeded, quickly leading inevitably toward race conditions manifesting unpredictably unpredictable timing dependencies complicating troubleshooting efforts, considerably increasing maintenance burdens, exponentially compounding operational overheads unnecessarily. Modern JIT-compiled virtual machines incorporating sophisticated escape analysis heuristics detect opportunities, transforming recursive formulations automatically into optimized iterative equivalents, eliminating manual intervention needs previously required painstakingly rewriting entire programs, transitioning from recursive formulations into equivalent non-recursive expressions requiring considerable effort, initially perceived as insurmountable obstacles, hindering progress until breakthrough discoveries unlocked novel pathways circumventing previous limitations, paving way forward, accelerating innovation trajectories, substantially enhancing productivity metrics achievable through combined synergistic effects realized collaboratively. Conclusion: mastering recursive algorithms requires deep understanding of base cases' vital roles in controlling execution flows, accurately determining precise moments when continuation ceases, becoming mandatory prerequisites guaranteeing successful completions, achieving intended objectives efficiently, reliably, consistently, regardless external factors fluctuating, dynamically altering internal states unexpectedly, possibly destabilizing otherwise stable configurations, threatening disruption unless adequately protected preemptively through meticulous planning, foresight exercised diligently throughout every stage of development lifecycle spanning conception through deployment, inclusive maintenance periods extending potentially indefinitely, contingent upon ongoing support commitments upheld steadfastly. By focusing intently on crafting well-defined base cases capable of gracefully handling exceptional circumstances encountered sporadically yet critically important scenarios demanding immediate attention, developers empower themselves to construct resilient systems exhibiting superior adaptability, responding adeptly, navigating shifting landscape demands, emerging continuously, reshaping industry standards, redefining expectations, regularly elevating bar higher, continually pushing boundaries further outward, ever expanding horizons, inviting exploration, venturing boldly beyond comfort zones, embracing uncertainty, confidently trusting competence cultivated, relentlessly honed, sharpened, refined over time through persistent practice, perseverance, persistence.